Okay, hello everyone. I will continue to present the result of the data-driven model in Guantao. And my talk will include a small introduction to the data-driven models, and then the method how to implement in the data-driven model. And then it shows the result from the Guantao. And finally, it's some summary. And first, I want to mention that why do we need to use the data-driven models again? So if you stay here last week or in the morning, you know that we can use the box model, numerical model, or even real-time model to do the groundwater level forecast. Why do we need to try another method? This is because the task of this project in the second phase is to upscale the method, what we used in Guantao, to some other regions. So in some other small regions or areas, there is less of these hydraulical investigations. So it's difficult for them to get some information about the parameters or to collect the data. So it's difficult to develop a box model or even a numerical model. But maybe in that regions, due to this easy installing observation sensors, they collect these data like the groundwater level data or the river runoff data for some years. And in that region, they are still want to do this groundwater level forecast or to make this to make the groundwater resources management. And based on this, and we tried the data-driven model in Guantao and to show that this is data-driven model could also work well to forecast the groundwater level. And the data-driven model is different from the box model and numerical model. It didn't based on any physical process. So we don't know what happened inside. So sometimes it's also called the black box. And it's not completely black box because it's also based on some mathematical equations. And they only learn from this, the data, what they collected. So that's based on this, now we shows the definition of this data-driven model. So it didn't explore, or man don't need to understand the physical behavior of the systems. And we just use this machine learning algorithm to analyze the data, what we collected. And we try to find a relationship from the data, what we have. And based on the new relationships, and we will make the predictions for the new data. So the whole process is the so-called the data-driven models. And normally there are three types of this machine learning method. And first, this is called the supervised learning. That means every time that you provide input, you need to give a notation. So that means each input corresponding to the output. So the machine will learn from this input and output to get a mathematical models. And based on this, and you make the forecast for the new data. So that means that next time when you give this grip fixtures to this machine, and he will tell you that it is a grip. And so normally what we used for the classification and the regression are both the typical way of this supervised learning. And another type is unsupervised learning. This means that we don't give output for any input. We just put the input data, all different kind of input data to the machine. And we don't tell them, this is an apple, this is a pear. But the machine will learn from this data, and he will categorize this fruit. So the apple will stay together. This is a pear or avocado stay together, and the orange will stay together. So the machine didn't know what's the name of this fruit. So next time, if you give an apple to the machine, and he will tell you it belongs to this type or this category, but what it is, so he didn't know. So the normally clustering problems or the dimensionality reductions belongs to this unsupervised learning type. And the last one is reinforcement learning. This means that the machine takes actions in a dynamic environment. That means he will learn from his experience, what he gained from the environment. That means all the actions the machines take, the environment will give a response, will give a reward or punishment. So from this, the machine learns that the next time he needs to do an optimized action for the environment. So this is a method is widely used in the computer gaming. And there are also a lot of machine learning algorithms available. So this is only list part of it. And which one is really good is really difficult to say. So for the real applications, it's still recommended that you try this different kind of learning algorithm to choose the one is suitable to your problems. So in Guantao, I tried this artificial neural network linear regression, and also the adaptive neural fuzzy inference system and the support vector machine. And all of these give us a more or less a similar result. So here we choose the support vector machines to do this groundwater level forecast. So it's also a bit more subjective to decide it, the machine learning method. The support vector machine is used to solve these classification problems. So it is a supervised learning method. So the goal of this support vector machine is to find or to define this hyperplane. This is surface, and to separate the data points. So they will maximize the distance between this surface and to the data points. So when this distance is large enough, that means we are easily to separate the different data points. And the support vector regression is a further extended application of this support vector machine. And it is used for the data regression analysis. And so in order to better explain this support vector regression, we compare with the simple linear regression. This is what is familiar to everyone. So for this simple linear regression, we try to fit the data points by minimizing the sum of these absolute errors. This absolute error means that this is different between the observations and the result what we calculate from these linear regressions. So we want to minimize this error. And the support vector regression is different. He introduced this is error band explore. So that means all the points, all the samples located in this band has no loss or there's no error. So only the samples located outside of this error band and has they call the losses is also an error. So the goal of this support vector regression is try to minimize the sum of these losses. So we only care about these samples located outside of this band. And the support vector regression not only can solve this linear problem, also can solve these nonlinear problems. How could they do it? They introduce a kernel function. A kernel function is try to project the data point what we collected in the low dimensional into a high dimension. That means that he tried to convert the non-linear problems in the low dimension to a linear problems in a high dimension. And here I take this classifications like the support vector machine as an example. So here this is two different sets. And this is a low dimension. If we try to separate these two data sets, you could say that the interface is quite non-linear. It's difficult to define it. But if we introduce this kernel function, we project this 2D data points into this 3D. And this look like these parabolic shapes. And we could say that these two different data sets can easily be separated by a plane or by a surface. So the support vector regression, like this linear regression, they need to define a weight and a bias, and from these data points what we collect. But besides the weights and bias, you also need introduce these kernel functions. So from this data, from this training process of the training data set, and we can determine this the weight and the bias, and finally to get the final equations for the support vector regression. And before start the training process, we also need to determine these hyperparameters. And these parameters is not the same like the weight and the bias, what I showed in the previous slide. It is a parameters we need to define in advance before the learning process start. We need to use this method to control the training process. So the hyperparameters we have in the support vector regressions, it is the error margin. So this is the error band, and also penalty factors. This is just introduced in this optimization process. That means all the samples located outside of this error margin or error band, they will have get a penalty. So the third one is kernel parameters. This is used to find these kernel functions. And all the hyperparameter values is determined here with this grid search method. And this is a simple method. That means you firstly predefined parameter range and also with a small subset of the values. And you try all these different combinations of the parameter, and then finally get a better one, which could provide a better result. And of course, there's also other optimization method to optimize these hyperparameters, and you can explore by yourself. And this implementations of these data-driven models is also easy. And firstly, you need to collect the data. So here you should collect as many data as possible, which is relevant for the groundwater level forecast, like the precipitation or the pumping rate. These are relevant. And then you need to prepare the time series, what you collected. And here I will explain a bit in details later. And after you prepare the data, you have to divide the data set you have into different data set. It's the training data set, validation data set, and the test data set. According to some of the rules, so the training data set should occupy 60% to 70% of the whole time series. And once you have this training data set, you will change the hyperparameters and use the SVR regression algorithm to train this model and to get the weight or to determine the weight and the bias of the equations. And use the validation data, and we will to evaluate the model. We compare the model result to the observations. If the result is acceptable or the error is smaller, and we will say that we have these final equations, it's fixed. And based on these final mathematical equations, and we will make the forecast of this test data. So we get the model forecast. And when the result is not acceptable, so we have to go back to the training data set to adjust our hyperparameters and to train the data again. So we need to repeat the process, and until we need to repeat the process and until you get a better result for the model forecast. And here I will mention this data preparation. That means we need to extract useful information, which is good for the forecast. Here is good for the groundwater level forecast. There's two different ways. First is the traditional time series decomposition. It will decrease the decompose the original groundwater level time series into the seasonalities and also the trend part. And finally, this is the noisy part. And another way is the wavelet transform. It is more powerful than the trend seasonality decompose method. It will decompose a time series into the different frequency or time domains. So for each of these sub-scale, and you will get the more specific or exact information for different sub-levels. And we use data informations for the further analysis. So it will provide more accurate and more specific information. And here what we used, it's called the maximal overlap discrete wavelet transform to decompose the time series. How did they do it? That means you put original time series xt, go through a high pass filter and also a low pass filter. Then you will get two different sub-time series. And this time series is also called the high frequency time series, and this is the low frequency time series. And the difference of this maximal overlap discrete wavelet transform from the original discrete wavelet transform is that he used this upscaling method every time when the time series go through the high pass filter or the low pass filter. So that means the sub-time series, what we get after the filters, had the same length like the original time series. But when you apply this discrete wavelet transform, they use a downsampling method. That means the sub-time series you get from here is only half of the length of this original time series. And at each level, when you want to go to the next level, you decompose the low frequency time series. That means the sub-time series from this low pass filter. And you will continue to put this time series goes through a high pass filter and a low pass filter, then get another two sub-time series at this decomposition level, and you will continue to decompose until they reach this maximal decomposition level, which is predefined. So you have to define the number before you start the decomposition process. And so this is maximal overlap discrete wavelet transform. It is more powerful than the, no, not more powerful, at least is more useful for the than the discrete wavelet transform in the applications to the hydraulic forecast, because he avoids the reconstructing process. If you use the discrete wavelet transform, you have to reconstruct the sub-time series to the original length. And during this process, you will use the data, what is happened in the future. That means if you want to reconstruct the time series at today or at this time step, and you need the data information at the next time steps. So this is contradict with this concept of this forecast. So that's the reason in the hydrological forecast, if you want to use this wavelet transform, we are recommended you use to use this maximal overlap discrete wavelet transform. And there's other details is presented in this articles. If you are really interested, you can read it. There's also provide some other examples to demonstrate why the peoples use the wrong wavelet transform in hydrological forecast. And after we choose or we collected all this data time series, and we need to select the important variables, which is related or highly related to the groundwater level. And here we use this mutual information, and it is try to measure the mutual dependence between these two variables. And it is not the correlation coefficient what we know normally. It tries to measure the uncertainty, the reduced uncertainty of one variable when you know about the other. And here, because every time we selected important features corresponding to the high mutual information, so that means we need to use this conditional mutual information. So if we selected one input features already, and then the next time we will calculate the mutual information of all the rest variables and the groundwater levels, and we will based on the selected input features, and then we choose this second important features, and based on these two, we calculate again the conditional mutual information of this the rest variables and the parameters. So this method is a filter method to select two features or the important variables to the groundwater levels. That means we first select these input features, and then we start to train the model using this training data set. And there's also existing other method like the embedded method or the wrapped method to select the features. And all the later two methods, and they need to train the model. That means the feature selection process is based on this training result. So this requires huge or large amount of computation. So that's the reason in practice, the conditional mutual information is more recommended or widely applied. And we also note that there's uncertainties in this in the data time series what we collected. Maybe you already know that when we mentioned the uncertainties, that means we need the samples. So for the data-driven model, we use the bootstrap resampling method to generate the different samples of the time series. And they use this random sampling method with replacement. And here I just show the example of the time series with the length 3. And here, this is the original samples. And based on this, you want to generate a new time series. So you will randomly choose one from these 3. So it could be any one of these 3. And here we choose it's the second one. Now it's the first time series. And after you choose this one, this data or these samples, it stay in the population. So when you want to samples for the next time series or for the next time steps, and you still sample from the 3 of these samples. So could be this one or could be this one. So here we choose this one. And then for the last one is also generate the samples from the initial samples. It could be repeated and also could be not repeated. So it means if you only have the length of 3 and you can only repeat 27 times, then it means you generate 27 different time series. And since we have these samples for the original time series, so that means all this training process, training, validation, forecast, we need to repeat n times. And every time you need to get a SVR model and then get a model forecast. And so finally, you will get this ensemble, this model forecast. And here, the model forecast, we only consider about the uncertainty in the data, what we collected. And here, we also need to pay attention to this model error. This is a model error that is means from this calculation. So you need to put these errors and into the model forecast. And then finally, you get these final ensembles of these groundwater levels. And here is how to quantify these errors in the model calculation. And here we use this meta-Gaussian method. And it is a statistic method. And it's trying to infer this or get the errors from this quantile plot. So this plot you will get from the validation dataset. From the validation dataset, you have a groundwater level, and you know that the error. This error is between the calculation and the observations. And then you draw this QQ plot. And for the forecast or for the test period, and you based on the testing data and make a forecast of the groundwater level. And based on this, and you could interpolate it error number. And then you put this error number to this model forecast, and you get this final ensemble of this groundwater level. It's not only including the uncertainty in the data, it's also included the uncertainty of this model error. After we know how to implement, and now we show that how did we really implement in Guantao. So here, first step is the data collection. And in Guantao, we collected this monthly data set from 2007 to 2018, and included this agricultural electricity consumption, because we don't know this pumping rate exactly, so we use this electricity data. And because highly electricity consumption, it means that highly pumping rate in Guantao. And then it's the precipitation data, and of course the groundwater level data itself is also important. Then is the surface water diversion. And we split or divided the data into the training data set. This is we use the time series between 2007 to 2015. And there is the 1 year data used to validate the model, and then test on the data from 2017 to 2018. And here we try to predict the groundwater forecast and different late times, like the 1 month, 3 months, and the half year. And here we show that the collect data time series is included the groundwater level, electricity, precipitation, and surface diversion. And we not only consider about the time series, we also consider about the delayed time series. That means like the electricity consumption, what happened in 1 month before, 1 month ago, 2 months ago, and until 1 year. And this is the same for the precipitation and the surface water diversion. Here we choose this 12 time lagged months is because we consider about their periodic changes. So every year they will change, or the dynamics will change a bit. So that's the reason we also consider about the delayed time series. And after we collect all the data, and we will use this wavelet transform to decompose our groundwater level or other input, and into this 3 different sub-levels, because here the decomposition levels, what we choose is 2. So this is high frequencies at level 1, and this is a high frequency time series at the level 2, and also the low frequencies of the time series at the level 2. So normally, the longer the time series is, the higher the decomposition level you can choose. And here, so the decomposition level 2 is good enough. And after decompose this time series, that means the original input, each original input corresponding to 3 different transformed subtime series. And this is the same for the each different data types. And if we put all these things, this time series together, that means the total input variables, what we have. is over 100. But that doesn't mean that all of these variables are important for the groundwater level forecast. So we need to choose the important features. So here, after applied this conditional mutual information, and we get the final selected input features for the groundwater level forecast at the different late times. So if we forecast the groundwater level at t time plus 1, so we only choose 4 features, and the important one is the groundwater level, and then followed by the electricity data. And for the groundwater level forecast at t plus 3 and t plus 6, the first important features is not the groundwater level, it is the electricity decomposed component from this wavelet transform. And you can see that we choose 4 features to forecast the groundwater level and next time steps, and we choose 5 features to forecast the groundwater level at 3 months in advance or half year in advance. Normally, that the chosen features should be less than 10 times of your input time series, and also that the finally number. So it's 4, 5, 6, and we need to define based on this sensitivity analysis. So that means we compared the result from the different number of the input features, 3, 4, 5, 6, and then finally we choose the one with the best result. So it's these features. And from the selected features, you could say that the electricity is only chosen from this low frequencies time series. That means during the selection process, the noisy time series is already get rid of. So that means the wavelet transform is also had the effect to get rid of the noise. So that it will help your information is more specific, is more exact. After we choose this, decide this input features, and we learn this SVR based on the training data set, and then we validate this model result and then forecast based on the test result. And this red curve, this is the ensemble mean of the training data set. The green and the blue is the validation and the test period. So from here, you can see that the root mean squared errors is increased from this training to this validation or test period. And the NASA efficient coefficient is decreased from this training data set to the validation or test data set. So this is more logical. And the higher the NASA efficient coefficient, the more accurate the model. And so from here, we can also see that during this validation period, our model can't fit the observations quite well, because that in 2016, it is wet year, there's a flood happened in Guantao. And in that year, the data what we collected may be not so consistent with the data what we collected before. So that's the reason there's a bit large errors here. Due to this model, due to the model error calculation is based on the result from this validation period. So that means here we have a bit larger uncertainty for this test data compared to the training data set or the validation. And the same trend we can also observe for the groundwater forecast and the time series 3 months in advance. You can see that the model error and the NASA efficient coefficient is also increased, and there's a validation period is not good, and the uncertainty in the test period is also larger than before, and this is due to this larger error observed in the validation dataset. And the similar trend is the same for the groundwater level forecast and half year in advance. So here you can also see that with the leading time increase and the model error is also increased. So that means the groundwater forecast and at the half year in advance is less accurate than the groundwater forecast at the time step of t+1 and t+3. And also this is the forecast with the lowest Nash efficient coefficient. And here we also compare the result from the data-driven model and the conventional or traditional alternatives applied in the hydrological forecast. So what is the conventional scenarios? It's first is this long-term average. So maybe we only take the average of all the data what we collected and to calculate for the forecast period. And the second, we use this multiple annual dynamics. That means we average for each month and we get the dynamics in a year. And the third one, we simply shift the time series. That means if we want to forecast the data or the groundwater level at t+1, we simply take the data what we collect at this time, at time t. And this is the last scenario. This is the ensemble mean of this data-driven model. And here I shows this root mean squared errors. You could say that the data-driven model provides the result with the less error. And if you look at the figures, so the long-term average, so the scenario 1, so that means it doesn't matter where you forecast, the value is the same. And for the multiple annual dynamics, for this is green. When this dynamics happened in this year, is faced to the historical changes, then the fitting is really good. And if the dynamics is changing and is far away from this historical dynamics, then the fittings or the forecast value is really worse. And so from here, you can see that our data-driven model could, because he used a bit more information, so he can also provide or forecast a more accurate result. Also compare the forecast for the other two time late, t+3 and t+6. And we also compare these different scenarios. The last one is the ensemble mean from the data-driven model. The first two should be the same because we use this annual average, annual average or the annual monthly average. So this is numbers is the same for the different for the forecast and the different time lates. And but if we use this shift away, so you could say that, and then the error become larger. That means the accuracy is really the model is not accurate anymore. And so from this table, we can say that the data-driven model still provides the most accurate result compared to these conventional alternatives. And all the method, what I explained here, is already programmed in R, and R software is totally free, and you can download from here, and you don't need to worry about it. You don't understand the method, how it works behind it, because all the functions are there. You simply call your functions and input your data, then you will get the result. So these data-driven models in R were easily for the beginners to start it. Here we also put all the whole data-driven models on this Shiny app, and you use one of these three browsers to open the link again. So I will stop sharing the presentation and to share the to share the. When you open this link, you will see that the data-driven model. And then you click on the data-driven model, and you will see that this interface. Here, this is which shows the sample size. You could choose from 1 to 100. And here you select this, the end time of this training data set, because I already fixed its initial of this training data set. It starts from the January of 2007. Like here, if you already choose one, you click show the result. Because this data-driven model is really running behind it or in the server, so it takes a bit time. And here you can see the result. And this is the training period. And this is the validation. This is the forecast. You can also zoom in to see that your forecast result. And then you can zoom out. And because here, once the training data set is fixed, and then the validation data set is 1 year after that. And then the rest are the testing data set. If you want to change to another shorter one, maybe we change to this 2013, or doesn't matter. And then you click the show result, and then the model will run on the server, try to, it's updates the result. You see, this is a training result, this is a validation, and this is a forecast. So, and here you can also change the sample size. Because of time, I only show a smallest number of ensemble size, right? And then you click the show result, and the model will run. So I think it will take 40 seconds something. Oh, now this is a result. This is a result with these different samples, and this is a training, and this validation. This is a forecast. I will zoom into this test period, and this is purple line. This is our sample mean, and then correspond to the maximum and the minimum, and then these observations. And if you are interested in it, and you can play by yourself. So the models is really running on the server. So if you choose a larger number of the sample size, so you have to be patient to get the final result. So now I go back to the presentation again. So come to our last part, the summary. Because these data-driven models try to get a relationship based on the historical data. That means if you want to forecast the groundwater level under some extreme conditions, it will be difficult to get accurate result. And these figures I also show that this is a river runoff forecast, and done by the Tobias is also a colleague in Hydro Solutions. And from here, you could see that the model is difficult to catch the flow peaks. So there's a large deviation between the calculation and the forecast. So this is the things we should keep in mind, that we can't predict the things we didn't learn from the historical data. So if you want to make the forecast more accurate to the peak flow, that means you need to create or collect a longer time series. There they included enough data showing this peak flux. Otherwise, you can't predict accurate forecast. And since we already explained so many different methods to do the groundwater level forecast, and in reality or in practices, how could we choose a reasonable model, a reasonable method? So here I just give some roughly information. And if we only have the groundwater level data, so we don't have any other data. And this, we can use these data-driven models to forecast the groundwater level. Maybe you also have collect other time series like the river runoff, and you could still combine the two and consider about the delay times to make another forecast using this machine learning algorithm, because more data included in, you will improve your accuracy of the model forecast. And maybe you included, maybe you already collect more data about this model parameters and have a bit more information about the local aquifers. And then you can apply this box model or the numerical models. When you have the more data, more details in times and space, then you can try this numerical model to do the forecast. And if all the data is available online, then we recommended you to run the real-time model, because they will give you the result, consider about all the different kind of uncertainty. The uncertainty is so important for the decision makers to make a decision. So the core of the message is that we should try our best to use all the data what we collected to make it useful for the groundwater level forecast. Okay, this is what I talked today. Thanks for your attention.